in the class today we will first review what we learned in the previous class through this PowerPoint presentation. In the first slide what I show here, and this is what we learnt in the last class, namely if the chamber pressure of the rocket is 5 MPa and the injection pressure is 7.5 MPa, and if there is a sudden dip in pressure by 0.5 MPa, then what happens is this sudden dip in pressure allows more fluid to come inside the chamber, and when more fluid comes inside the chamber it does not burn instantaneously, but it takes a small time. Tc is what we defined in the last class, namely it takes Tc time to burn, and when it burns, since more fuel comes inside or more propellant comes inside the chamber, there is an increase in pressure. After this decrease there is a time decrease and thereafter the pressure increases. In other words, during this time additional propellant has flown in the chamber, and because when the pressure has increased, when the pressure has gone up, the pressure drop across the injector has now decreased, therefore less quantity of propellant now flows and it burns. After some particular time little less pressure is generated and we got a pressure oscillation like this. In other words, when the injection pressure was 7.5 MPa and the chamber pressure was 5 MPa, we progressed and found that when there is an initial drop in pressure by 0.5 MPa, then after some time the pressure increases from 5 to 5.5, again decreases from 5.5 to 4.5, and this sequence of oscillation continues. We would like to see what happens when the pressure changed. We changed the pressure, injection pressure, from 7.5 to 7, and when we did that, what did we find? For the same value of the combustion delay time, we started with a pressure drop from 5 to 4.5. When this happened, we had additional propellant flow which was 1.12 times the nominal value of flow corresponding to 5, and for this value, since the flow rate is higher and it took some time to burn, when it came over here you got additional gas getting generated in the chamber, and this led to an increase in pressure. This higher pressure led to starvation of propellant inside it, and therefore after some time the value, that means the propellant flow rate decreased. When this came up you had a net decrease in pressure, and what did we find? That the pressure amplitudes kept on increasing with time. We also did one exercise wherein we had the injection pressure at 9 MPa, and what did we find in this case? Instead of repeating the whole thing, we started with a pressure drop up to 4.5. After a delay time, because of the decreased propellant flow or because of the decreased pressure, increased mass of propellant flow into the chamber, pressure again increased, but the pressure increased to a smaller value and the successive values kept on decreasing. In other words, in this case you had the pressure amplitudes decreasing with time. In the earlier one you had pressure amplitudes increasing with time, and still in the earlier one you had neutral level of oscillation, that means pressure amplitudes were constant. We also went ahead and tried to find out what is the reason for these changes, whether we could find it out through some expressions, and therefore what did we say? We said that the rate at which mass increases in the chamber, rather dm by dt, is the rate at which the propellants gasify, that is m dot g in the chamber, minus the value at which the gases leave the nozzle, m dot n. We wrote these expressions in terms of delayed combustion time. In other words, what is it I am trying to tell you? The gases which are generated are not corresponding to the propellant which is getting injected, rather the mass which gets generated comes from propellant which is injected Tc earlier. As you will recall, if I go back to the previous slide, now when the pressure drops the propellant flow increases, but this propellant flow has increased over here. It takes a Tc time to gasify. In other words, there is a delay in time, and therefore the quantity of propellant which has flowed Tc seconds earlier is what contributes to the pressure, and therefore dm by dt or accumulation of mass in the chamber of the gas is corresponding to liquid propellant flow is dm by dt is equal to m dot p, that is liquid propellant flow Tc seconds earlier minus m dot n. You will also recall that m dot n we expressed as Pc80 by C star, and therefore now we would like to solve this equation, but this equation as we noted was rather clumsy because a time effect came over here, and therefore we want to simplify it. And what did we do? We wrote mp dot T minus Tc, namely mp dot is equal to, in the case when the chamber pressure is Pc, the discharge coefficient of orifices and the total area of orifices is A0, discharge coefficient of orifices is Cd, m dot p is Cd A0 into 2 of the density of the propellant into P injected minus Pc, this is the injection pressure drop, and therefore I could write dm by dt, m is equal to PV by RT, therefore I could write m is equal to PV by RT assuming T as a constant is equal to Tc. I get dm by dt is equal to dpc by dt is equal to, here I get RT and Vc, I bring it on the right hand side, I get dpc by dt is equal to RTc by Vc into this value of propellant injected Tc time earlier minus the one leaving the nozzle as 1 over C star RTc by Vc into Pc by At. We want to solve this equation, and how did we go ahead with it? We told ourselves we are interested in finding out whether the oscillations grow or decay, therefore we express the chamber pressure as the mean chamber pressure, that is Pc bar, plus the perturbation. Rather we had the term in which propellant mass is there, we had RTc by Vc CdA0, we had P minus Pc, therefore this P minus Pc is at T minus Tc, we could write it as P injected minus, here we said Pc is equal to Pc bar plus P bar, rather P injected minus Pc into 1 minus P bar, that means P injected minus Pc minus P bar, and that is what this expression tells you, RTc by Vc CdA0 into 2 rho into P injected by Pc and minus P bar over here at time T minus Tc. Now we note that this value is corresponding to the steady chamber pressure, and this steady chamber pressure corresponds to the steady value of mass flow rate through the nozzle, namely 1 over C star into Pc over At, and therefore the expression which we had for dpc by dt could again be written as, maybe we are saying that this is equal to 1 over C star Pc At, and therefore we also had the expression for, let us say that the mass, that is the value of chamber pressure is here, the At is here, we could write it as gamma squared C star by L star into Pc bar, that means you had this value, and this value over here into 1 is the steady value which is Pc bar minus the value of P bar into this to the power half minus the value leaving through Pc over here. How did this come over here? We had the value, you will recall if you go back to the old slide over here, we had C star is equal to under root RTc by capital gamma, therefore RTc is equal to C star square divided by gamma square, and this is what is substituted subsequently to get this particular expression over here. We wanted to solve this equation, and how did we solve this? We said, well, we will define residence time, we derived the expression as a function of L star, that means the value of Vc by At divided by C star by gamma square, and therefore we got the final expression as dpc by dt is equal to Pc bar by T residence time, that is the time spent by the gases in the chamber, into I take the under root sign, I take the first term, I know my P bar is small, therefore I write it as 1 minus half of P bar by P injected minus Pc bar minus what I get on the right hand side, namely the value which I took here, gamma squared C star by L star, I put it in terms of residence time and I get Pc by T residence. However, since Pc is equal to Pc bar by P bar, and I can also denote the amplitude of pressure oscillations in a non-dimensional manner as P bar by the value of Pc bar, I substitute instead of writing P bar and P injected minus PC bar and PC bar, I substitute the value of PC over here in terms of PC bar plus P bar or 1 plus phi into PC bar, and what is the expression I therefore get? I get the value as dPC by dt is equal to PC bar by T residence into 1 minus the value of beta, and this beta I substitute in terms of PC bar divided by 2 into P injected minus PC bar. Let us go back to the old one. I denote this particular expression, or rather P injected minus PC bar, I take PC bar by PC and therefore I get PC bar on top, therefore P prime by PC bar is equal to phi, and I get PC bar on top, therefore PC bar by P injected minus PC bar, and that with a 2 here is what constitute my value of beta, and I get a value of dPC by dt as equal to PC bar by T residence into 1 minus beta into the value phi, which is P bar by PC bar at time t minus Tc minus PC by T residence. In this way I am able to incorporate the value of time into the equation, that means the value of t minus Tc corresponding to this, and now I solve this equation and therefore I simplify it and I get the value of, now I get PC is equal to PC bar into 1 plus P prime by PC bar, which is what we had earlier. PC bar is equal to PC is equal to PC bar 1 plus phi, and now if I substitute it here I get the value of d phi by dt plus I get phi by T residence is equal to minus beta of divided by T residence into phi. I need to solve this equation, and now I have been able to incorporate the earlier time of fuel injection into this equation, and when I solve it, and how do I solve it? Well, I assume a form phi as equal to a cos omega t, which is real part of a into e to the power I omega t, and I know omega is equal to 2 pi of frequency, and therefore if I say the oscillations grow with time, well, phi is equal to the real part becomes a e to the power alpha t. If alpha is greater than 0, well, the oscillations grow in amplitude, and therefore if I denote phi as equal to not only in terms of frequency omega but also in terms of the growth of oscillations, I can write phi as equal to a e to the power of the growth rate of oscillations and the frequency of oscillations, namely phi is equal to a e to the power alpha plus I omega t. I substitute this expression in the earlier expression, namely over here, and now I get the value as d phi by dt plus phi T residence is equal to beta T residence into phi T minus Tc. I substitute the value of the expression which involves phi in this particular form over here, phi is equal to a e to the power alpha plus I omega t, and I separate the real and imaginary parts. This is the real part of the equation and this became my imaginary part of this equation. Now I need to solve for the real and imaginary parts, and what did we do? Well, let us not solve it for the total, let us solve it for the critical case for which the waves do not grow, that means alpha is equal to 0. I substitute alpha is equal to 0 here and I get this equation becoming 1 over T residence is equal to minus beta over T residence into cos omega t. I put alpha is equal to 0 here, I get omega is equal to beta over T residence into sin omega Tc, and this I further simplify. Since I have cos omega Tc and sin omega Tc, cos square omega Tc plus sin square omega Tc is equal to 1, I can write this expression as equal to, or on the right hand side, sin square omega Tc plus cos square omega Tc is equal to 1, or rather I get omega t residence square plus 1 is equal to beta square, or rather the circular frequency squared is equal to beta squared minus 1 divided by T residence square. I also get from the second equation here, I can now write the value at Tc, that means I get the value of cos omega Tc as equal to 1 over T residence cancels, it becomes 1 over beta minus 1 over beta, which means it is minus, it is in the third quadrant, and therefore I can write cos or the value of secant of this as equal to secant of omega Tc is equal to minus beta t, or the value of omega Tc is equal to pi minus tan inverse beta square minus 1. Now I combine these two equations, I get the value of Tc from this particular expression, T residence from this particular expression, and then I put the value of Tc by T residence, because it gives me the value pi minus tan inverse under root beta square minus 1 divided by under root beta square minus 1 over here. Now what is it I find? I get this critical value, this came for alpha is equal to 0, for alpha to be less than 0, well, the value should be less than this, and based on this we plotted the stability diagram. And what was the stability diagram? We got this expression for Tc corresponding to alpha is equal to 0. If alpha is less than 0, the value is over here, that means it is stable. If alpha is greater than 0, this corresponds to the unstable part, and this is what we learned to do. Now when I want to get the value of the injection pressure drop as a function of chamber pressure drop, let me go back to the previous equation for large value of this. If I go over here and if I say my combustion delay is infinity, rather Tc by T residence is very large, the value of my beta is equal to 1. This is under the condition that the combustion delay is very large. If I want the value at Tc for a very large value, that means beta is equal to 1, then I get, but I also know that the value of beta is equal to Pc bar by this, therefore I will get neutral oscillations, or the condition under which pressure amplitudes do not grow corresponds to the value of P injected minus Pc bar, which I denote by delta P injection, divided by Pc is equal to half. It will be stable when it is greater than 1, because I took the inverse for beta, therefore I get delta P injected by Pc must be greater than half for stable, and if oscillations have to grow, delta P injected by Pc must be less than half. And this I follow up, and now I say if the value of Tc is not infinity, then what happens to the value of beta? You go back, yes, this is for infinity when beta is equal to 1, when Tc has a finite value and keeps on decreasing, the value of beta keeps increasing. If the value of beta keeps increasing, well, for large values of beta, now I find that the injector pressure drop, which is very much smaller than the value what I specify, is adequate, and that is what I will be examining further in the course of my talk today. But I also find that the value of omega Tc from the previous expression comes out to be pi minus tan inverse under root of beta square minus 1, rather as the time delay increases, my frequency of oscillation decreases. To summarize then, if I have, instead of one propellant flow, if I have propellant flowing at a mixture ratio capital R, well, for the condition under which Tc is infinite, I have delta P injector for the oxidizer divided by Pc is R by 1 plus R, and for the fuel I get 1 over 1 plus R. That means these are the conditions which must be satisfied for stable performance when the value of Tc is infinite. When the value of Tc is finite, well, a much smaller pressure drop is adequate to ensure stability. This particular criterion was developed by Summerfield, and it is known as Summerfield criterion. So let us quickly summarize where we were. All what I am trying to say is, well, under certain conditions a liquid propellant rocket shows severe oscillations, and these oscillations in chamber pressure and therefore the thrust is what we call as combustion instability. The plot shows the chamber pressure as a function of time. You see that the chamber pressure, instead of being constant at about 30 bar, fluctuates between 24 and 36 bar. The magnitude of the pressure oscillations increase with time and thereafter get saturated. And when you look at these oscillations, you find in the previous plot, if I were to take a look at this, I find this is the duration of my, this is the frequency over here, this is the time of different instants over here. I find this is frequency of the oscillations. This is known as a waterfall plot, in which I plot the amplitude of the oscillations as a function of the frequency and as a function of the time. This is at 0 time, motor has not ignited. it has just got ignited, I get an ignition peak and I get a small oscillation here. After some time, maybe at 1 second, I start getting some oscillation here, and then it at a frequency of around 100 hertz, and then for higher frequencies I get no oscillation, and this 100 hertz oscillation is seen throughout till the motor sort of dies down over here. That means I have frequency of 100 hertz, and in which these are typical ways of representing the instability, wherein we plot the amplitude of pressure oscillations as a function of time going in this direction for different frequencies over here. We have an injector, you have a combustion chamber and the nozzle, you are injecting something over here, and what is it? If I were to denote it, I say I have an injector over here, and what happens after injection? I have the process of atomization taking place, atomization, then I have vaporization of the propellant taking place. After vaporization I have mixing taking place, after mixing I have chemical reactions taking place, and then the gases leave through the nozzle, right. Now in a bipropellant injector, that means when I have fuel and oxidizer, maybe I have a fuel injector, fuel holes, I have oxidizer holes over here, I call it as injector over here. The fuel injector maybe creates the fuel drops and it vaporizes first, it vaporizes, the oxidizer drops vaporizes, the vapors come and mix in the chamber, maybe this is also in the chamber, but thereafter you have mixing and reactions taking place over here, and the mixed one is what gets injected out of the chamber. During this process of combustion, if there is some oscillation, namely P prime, it gets back into your injector over here. This is where you are injecting P injected, you are injecting P injected over here. This P prime gets modulated in your injector, and therefore you are getting some change thing which is coming into your chamber again, your vaporization gets affected, and this becomes something like a feedback circuit. In other words, a change in the downstream value of P prime due to mass generation gets coupled to your intake to the injector. That means it is the feed system which gets affected, and therefore this type of combustion oscillations is known as feed system coupled oscillations. Let us now physically try to again go through what little we have done so far in some other way. We will tell ourselves, well, I have something like a tank which supplies the propellants into the liquid propellant combustion chamber, fuel, oxygen, I do not draw any of the intermediate things, all of us know the differences. I have an injection pressure here, I have the injector here spraying it, I have the PC over here, I have the injector pressure over here, I take the same values on both the sides, and now what is happening? Any pressure changes which is happening creates a differential flow over here. In other words, this is what gives me the feedback, that is the pressure changes here reflects on the flow of propellant into the chamber from the feed system. That means feed system is influenced, and such type of oscillations are known as feed system coupled oscillations. Therefore, it is known as feed system oscillations, or rather the oscillations depend terribly on T residence and time of delay. T residence depends on the L star of the motor, therefore some people also call it as L star oscillations. In other words, all what we have seen is, it is quite possible when I have the injector pressure drop which is less than some threshold value, then it is quite possible for me, instead of having a steady value of pressure, to get started and have a diverging pressure. And these oscillations are linked to the feed system, because the feed is what gives you the pressure drop over here. If I have a very high pressure here, I will not get these oscillations, and therefore it is known as feed coupled oscillations or L star oscillations. Maybe we should go through it again in some way, maybe we should go and look at the derivation and what we derived the results, but something I want to caution you, which many people wrongly use. We derived the expression that maybe the value of injected pressure drop, that is delta P injected, to the value of Pc bar must be less than equal to half for oscillations to occur, but this condition is true only for the condition that Tc by T residence is equal to infinity. How do I explain this? Let me get back to our stability diagram in which we had Tc divided by T residence as a function of we had the value of beta going from 1 to infinity, and initially for very large values Tc infinity we had this value, and we had this boundary which was given by pi minus tan inverse of beta square minus 1 divided by under root beta square minus 1. What did we try to get? We found out the value for the condition when Tc is infinite, or rather it is the value of beta is equal to 1, for which we said beta is given by the value which was equal to injection pressure drop, or rather 1 over beta, and therefore we had the expression as delta P injected divided by the value of Pc was equal to half for this particular case, or rather we said that when Tc is very large this becomes my stability criterion. However, when Tc is less the value of beta is larger, and when beta is larger, well, the value of delta P which I can take is going to be much lower than alpha. This was my stable region, and therefore a much lower value of injection pressure drop will give me stable operation when I have smaller values of Tc correspond instead of the infinite values corresponding to beta is equal to 1. Let me repeat this again. All what I am saying is when Tc goes to infinite, we are talking of Tc by T residence also of going to infinity, or rather beta is equal to 1. When Tc is smaller, well, the value of beta is larger, and therefore a smaller injection pressure drop will be sufficient for me to provide stable operation. If your chemical delay is a small number, well, I need a smaller injection pressure drop to avoid oscillations, and this we also saw. We saw when Tc was 0, well, there is no question of any oscillation at all. Therefore, the feed coupled oscillations or L star oscillations are a function, we must remember, of not only the residence time and the value of Tc. It is because it is a function of Tc, it becomes a nature of propellants. Maybe if I have propellants which are sluggish like aniline and red fuming nitric acid, it is more susceptible because they have a larger delay. I think this is all what I will do in these feed coupled oscillations with respect to liquid propellant rockets. Now let me see whether I can get similar things for solid propellant rockets. Let me do a simple argumentative explanation. Let me consider the case wherein I have, let us say, a solid propellant rocket. I have a propellant over here which is burning. We will try to go through the same arguments I put for liquid propellant rockets. Let the chamber pressure be Pc. This is, let us say, a section over here is the propellant grain, outer diameter. Let us say the chamber pressure is a high value, steady value burning, it is progressive, maybe it is going to go up, but it is a progressive steady value. At some point of time, let us see that the pressure drops, some way pressure drops, let us say. If the pressure drops, what is going to be the effect? Would I have a cascading effect like what I had in liquid propellant rockets? If I have a Tc over here, a delay. Let us see what happens when pressure drops. The heat from the gases is still seeing the propellant, that means the propellant surface is still hot and it has a memory of the higher pressure over here. Higher pressure means the flame is nearer to the propellant surface, therefore more heat is generated and therefore the propellant surface gets more heated than at lower pressure. Therefore, I find yes, when the pressure is higher, maybe the heat flux or the heat load on the propellant is higher, even though the pressure drops, it still retains memory of the old pressure and it does not immediately relax to a lower heat flux at the surface. That means I say point 1 retains memory of old pressure, old value of higher pressure, old value of pressure. Number 2, the pressure has dropped. If the pressure has dropped, what is going to happen? The flame front, that is the distance of the flame from the surface goes a little bit further, and since the pressure governs the number of molecules, the rate of reaction decreases. If the rate of reaction decreases, well, the rate of generation of hot gases decreases, or else the velocity decreases, and if the velocity decreases, the residence time increases. Let me go through this a little more in little more detail. All what we said was, whenever I have a propellant surface, I have a flame which is standing off at a certain depth. I reduce the pressure, therefore the flame standoff increases, but the surface still has memory of this. This is point 1. Now this has gone up over here, the pressure has decreased. If pressure has decreased, the chemical reaction rate has decreased. If chemical reaction rate has decreased, the rate at which mass of the gases is getting generated has decreased, the velocity has decreased. If velocity has decreased for the same distance, I get more residence time has increased. If residence time has increased, the time taken for chemical reactions to get completed is faster, therefore residence time increasing results in more value of the rate of mass generation. Now the surface still retains memory of the past, it is still hot, therefore it is still producing gases at the old rate, and therefore even though the pressure has fallen, it takes some time for the surface to come back to the present state, and therefore what is going to happen is the pressure increases because I still have more mass of gases which are going up, I have higher mass flux rather than this value, and therefore I get a higher value of pressure. At higher value of pressure, well, what happens is the memory of the surface is with respect to the older value of pressure, for which the mass generation rate is lower, the residence time is less. If residence time is less, I have smaller chemical reaction time to generate gases, and therefore it again falls back. Again I have this, and therefore the same thing is possible even in a solid propellant rocket, namely whenever there is a delay due to the thermal lag at the surface and we have the residence time getting changed, I can get this oscillation, and this is known as L star oscillations in solid propellant rocket. Why do I say L star? It depends. If I have a very small rocket in which the value of volume by throat area is small, well, the value of Tc compared to T residence will be larger, and therefore the oscillations are more profound, and that is why it is known as L star oscillations. Let us focus on this particular slide over here. In this slide I show the value of L star as a function of chamber pressure, and I define the regions of instability, that is L star mode of oscillations, and the stable region. What is it we are telling? If the value of L star is small, well, the time of residence of the gases, T residence of the gases in the chamber is small. When T residence is small, the value of Tc by T residence is larger, and therefore the combustion is more likely to be unstable, and therefore I have the instability region corresponding to small values of L star. If the chamber pressure is smaller, the chemical reaction time is larger, the chemical reactions take more time to go to completion, Tc is larger, and therefore I have an instability region which is over here and a stable region corresponding to larger values of L star and larger values of chamber pressure. Therefore, we find that for solid propellant rockets it is necessary to provide either a large value of L star or a large value of chamber pressure for stable operation to take place. Let me go and illustrate this further. Maybe if I have an L star instability, I have oscillations in chamber pressure which are seen over here. This is L star instability, but very often we also find that when a motor is ignited and the ignition is not that good, we sort of get some spikes like this. This is the ambient pressure, and you get a small spike in pressure, the motor gets ignited but gets quenched, but however the motor grain is still hot, and thereafter this heat or the temperature in the grain again ignites the motor, and again I get another pressure spike, another spike, something like a train going chuffing all along, chuff chuff chuff. You get these small oscillations in pressure which are due to ignition and hang fire situation rather than L star oscillations or L star instability which occurs when the chamber pressure has a finite value. This will help us to differentiate between L star instability and chuffs which are essentially due to an ignition phenomenon, not a good ignition, whereas L star instability comes because of the competition between the chemical reaction time and residence time. When the time is large and you have these reflexes from the propellant absorbing energy and getting delayed, that is where you get the L star instability. Well, I could have a motor in which I can vary my V star Vc, that is the chamber volume for a given throat area, get different values of L star and operate it at different values of chamber pressure. I have a propellant here, I have a movable piston by which I modify my volume for each of the experiment, and therefore I operate at different values of L star, different values of pressure, and thereafter I can get my particular plot, and this is how we define the L star boundary. This plot is fairly linear for most of the cases, and we say, well, this is the instability region, this is the stable region, this boundary in the plot of L star versus pressure defines or gives me the boundary between stable operation and unstable operation for L star oscillations. Something which I thought I should at this point in time I should differentiate is, maybe whenever I talked in terms of feed coupled oscillations in a liquid propellant rocket or in terms of L star oscillations in a solid propellant rocket, all what I am saying is the pressure in the chamber or within the grain, at this point the pressure is the same, at this point the pressure is the same, at this point the pressure is the same. Within the chamber the pressure is the same, there is no variation in pressure. That means I am talking of maybe the entire bulk of chamber has same gas pressure. What did I do? I injected something at P injection, I have Pc over here, Pc, and it is exhausting out. That means the entire volume or the entire bulk of propellant is at the same pressure, and therefore such oscillations are also known as bulk oscillations. Something very similar to the toy I showed you, the entire body is moving, it is not that one part, not that my hand moves and the other hand is stationary. But in practice what happens? I could have a different pressure here, I could have a different pressure here, and that is what happens when I talk. I am talking to you, and as I am talking, it takes some time for my signal to reach you. Therefore, it is quite possible pressure, instead of being a function of time alone, could be a function of distance and time, and therefore whatever we have discussed so far relates to something like a lump mass assumption, wherein I take the entire volume to oscillate in unison, which may not really be true. Therefore, we must move to something which will differentiate between pressure at the different points. Let's think of this situation, how easy would it be to do that. Maybe we will illustrate it through some physical examples. Let's consider the following. Let's consider, let's say maybe I am talking to you some acoustic oscillations. Maybe I am talking over here. How does the signal come to you? A series of compressions followed by rarefactions, followed by compression, followed by rarefaction, right? In other words, if I were to plot it, what is it I get? I get a region wherein I get compression followed by rarefaction, compression followed by rarefaction. In fact, this is something as a sound wave. And how do I represent pressure? As a function of time. And I can now write, this is a sine wave after all, this is one cycle of oscillation, that is one wavelength of oscillations, and this is my distance. As distance moves, my compression, rarefaction travels, and therefore I can write this as P is equal to maybe some amplitude A sine of lambda corresponds to 2 pi by lambda into x. This is the equation to a sound wave which is propagating, and sound wave means a disturbance wave. P prime is equal to P hat or A sine 2 pi by lambda x. But there is no travelling component in this. This is just a wave of compression and this, but I was telling you that the wave travels. If the wave is going to travel at speed of sound, that is A meters per second, where A denotes the speed of sound, well, after, let us say, after a time t, after I start, the wave should come over here, right? That means over a time t, the wave would have moved a distance at, where A is the velocity of sound. If that is the case, the equation to a travelling wave should be P prime is equal to A sine 2 pi by lambda into x minus at, right. Now what happens? Now when I look at this particular thing, and now I tell myself, in a rocket chamber, what is a rocket chamber? It is something like a cavity. Why do I say it is a cavity? Well, I have the injector side over here, or head end of a solid propellant rocket. I have the nozzle over here. We found there is very rapid changes in density here, therefore the throat acts as if it were a surface itself, and therefore whenever some wave travels up over here, this looks at it as if it was a solid surface, it reflects back. The wave is as if it were in an enclosure in which wave moves up over here, reflects over here, comes back, and therefore there is an interaction of, let us say, an incident wave plus a reflected wave. But I know the equation to a wave can be written like this. Now what will be the equation to a reflected wave if the incident wave I say is Pi is given by this? The equation to a reflected wave should be, it is moving in the opposite direction, therefore it should be A sine of 2 pi by lambda into minus x minus at, or minus A sine 2 pi into x plus at, and this is what we will be looking at in the next class. We will be trying to see whether some wave motion is possible in the chamber and what it could lead to. But as a prelude to this, I want us to think a little bit more, and the thinking is, maybe I brought a flute. I always illustrate combustion instability problem through this. I have something like I blow into this. Why does it make noise? Why should a flute make noise? After all, I am blowing steady, still it makes a noise. Similarly, if I have a whistle is nothing, similar thing at the what is where I am blowing, I blow into this, it still makes noise. Why does it make noise? Let us try to understand this problem as a prelude to solving this, and if this part is clear, maybe we will be able to relate it. Let us schematically show a flute and ask ourselves what happens. After all, you have something in which I am blowing air, I have something like a step over here, Let's be very clear about it. I have something like a step over here, I have some holes here. What is it I do? I blow air here. When I blow air, I get some eddies because all of a sudden there is a change here, some disturbances are generated, and when disturbances are generated they move in the chamber over here. It sees an open part here where it gets reflected back, and therefore a column of interaction between the forward running wave and backward running wave is created, and that creates some resultant wave which amplifies the sound. And if I were to plug one, let us say I plug all the holes here, I have something like 6 holes, I plug it, still it makes noise. That means, but it makes a different sound noise, in which case I just have a chamber here in which something is happening. When I open something, my net reflection is somewhere earlier, and therefore I can change my character of wave formed by incident plus reflected disturbances. And exactly the same thing happens in the case of a whistle. What happens in the case of a whistle, let us say, let us sketch it out. You find the same phenomenon in this. I have a hole here. What is it I do? I push air, it creates some disturbances here, some disturbances are generated, I have the waves moving in round like this, and it is this which functions as a resonator. And why does it resonate? I have forward and reflected waves coming. In other words, when I have a chamber, I could have waves not only moving in this direction, but if I take a section, I have a cylindrical section, waves could also move in the tangential direction, waves could also move radial direction, and this is what leads to disturbances in a chamber. And if these disturbances were to couple with the combustion taking place, well, I could have instability. And therefore in the next class I will start somewhere here, maybe we will take a look at this reflected wave, we will take a look at the incident wave which was equal to A sin 2 pi by lambda into x minus 80. We will solve for the resultant wave, and based on that we will try to get some more idea of instability, what could take place. After this is over, we will go into the process induced instability, something like pogo, something like sloshing and stuff like that. Okay. Well, thank you then, I think we should break.